everyone to the third session of the Legacy of Socrates. Now we're having Carola Lilienthal. So Dr. Carola Lilienthal is a managing director of workplace solutions in Germany. In 2015, she has summarized her experience with many code bases, legacy systems, like more than 100 analyses she did in one book, Sustainable Software Architecture. Personally, I've heard about Carola in the podcast of Legacy Code Rocks podcast, which if you don't know, I recommend you go have a look. And she did talk about how to improve legacy system at DDD Europe in 2019. And today she is giving that talk, how to improve a legacy code base remotely. So thank you very much, Carola, for being here.
It's a pleasure for me. Thank you, Nicholas. Hello, everybody. Yes, I want to talk to you about how to improve legacy code. And I'm a big fan of looking into old systems, how they have been built and what people thought about it, how they imagined the architecture to be and how it changed over time. And I put on this first slide a little joke. I love a lot jokes about software and architecture, and this one is about a good architect leaves a footprint, and then there are a lot of layers, and one person says to the other, "We gave up finding proper names for the layers long ago. Since then, we just name them after their architects." And if you follow the layers upwards, you see transformation, transport, David, Mark, Julie, and John. So this is how it goes if you don't improve your legacy code base every now and then, but you just stay with the names of your architects. And anyway, the nice thing about this joke is there's a female architect in there, and I'm in a company that really tries to have female software developers in our team. So here you see my whole company, Workplace Solutions. We are 120 software developers now, and we have a lot of fun with new code bases and with old code bases. And Nicholas already mentioned my book. My German one is already 5 years old, and the English one came out last year. And I will tell you some stuff out of this book. And the main thing actually is to find out what can we do to improve legacy, to get it back on the path of virtue where maintenance really gets fun again. And I try to get this whole thing into one diagram, which I will show you now, how software gets to become legacy that is difficult to change and where we don't have a lot of fun maintaining it. So imagine you had the most wonderful development team, a cool product owner who really knows what he wants, a management that understands that software development costs some money and that you need time to think about the concepts and redo things. If this is what happened, then in the moment that you release your software the first time to your customers, to your users, we think we hope that our software is in a good shape and has a low number of technical depth. Technical depth is sort of the thing that happens in legacy code. They get more and more depth in there, and the software gets more and more hard to change. And if we are lucky, if we are really lucky, we start on the left side where the technical depth is low. And if our software is a good system, our users will start to use it a lot and find bugs and think about new features that they want. And we start to enhance the system. And the solutions that we find in the first moment are not the best ones. I think you know that in software development that this happens a lot. So we get some technical depth into our system, and this is what the yellow arrow tries to indicate. Our software is gathering some technical depth, and when we have a good management team and good technical leads, we will find time to refactor this after a while. So the green arrow goes down again, and then the yellow one again, and we start to have a kind of a curve and rest in a corridor of low and stable maintenance cost. And this is where everybody wants to be. This is a good legacy system. After a while, every system tends to be legacy because it's old and many people have done something about it, but the maintenance cost is low. And this is wonderful if we can stay down there. But normally, with most systems, life is different. We start to change things and the yellow curve starts to go up and to get red even, and the arcs get smaller and smaller. And this is to indicate that with the same amount of time or budget, you can construct less and less. You can get less and less functionality out of your team. And in the end, you arrive in the uppermost corridor with high and non-predictable maintenance costs. And this is really where people are suffering, development teams are suffering, and where people ask the question, what can we do? How can we improve our legacy? And of course, to improve legacy, you have to refactor to get downwards again into the corridor of low and stable maintenance cost. Some teams can't even go down with refactorings and they just replace the system. This is the turnaround to start over and over again. But this is rare today. Most systems are valuable. They stay around and you have to refactor them to get them into a better shape. And quite often people call me and say, well, Carola, can you come by and help us? We have such a problem with our system. We can't maintain it anymore. It's so hard. It's so difficult. And I searched for a picture to tell people how they feel. When I get there, I see a team that feels a bit like this tree here on this slide. They try to survive. They do everything they can in the development team to keep the system up and running. They get up at night to restart servers and to delete long log files or whatever they do. But the management looks from above, and from above, the tree is green. And the management says, well, it works. You can do it. You did it last week, so you can do it again. Why are you complaining so much? And this is often my role to explain to the management in what condition their software system actually is. And I have looked at a lot of systems in Europe, some as well in America, in the last 10 years already, I think. And we have looked at a lot of different languages and different sizes. So the largest system I have ever had in my hands had 15 million lines of code, which is really, really huge. A lot of systems are around 500,000 lines of code. A lot are around 1 million, 3 million, 5 million. So there are really, really big systems out there in all different kinds of languages. And this size is so huge, the size of some systems, that people can't grab the whole or work on the whole. The other day, someone called me and said, oh, Carola, can you please come? We have a problem. And I said, well, what do you have? And on the other side, the architect says, well, we have 3 million lines of Java code. I said, yes, okay, 3 million is quite a lot, but what is your problem? Well, we are doing maintenance all the time. We can't enhance the system anymore. And I asked him, well, how many people are programming this 3 million lines of code, working on it? 30 people, he said. Oh, I said, well, this is a lot for just maintenance. You should need 10 people for 3 million to do the maintenance, and the rest should be able to enhance the system, to create new features and all that. So we went there and we looked at their system, and I'm going to show you some pictures of what we found in there later on. The big problem with software systems and architecture is that we spend our time, if we try to enhance or change a huge code base, most of the time we spend with code comprehension. We try to understand what's going on in this system. What does this structure mean? Why are these classes connected like this? Why are there these objects and those objects, and what are they doing together? And this is the main point with legacy code. We have to to construct our systems in a way that people searching in the code base for a solution or for a problem quickly find their way around. And well, if we need so much time to understand, I looked into cognitive science to find out why this is the case. Why do we need so much time to understand huge structures, or what can cognitive science tell us about understanding huge structures? What does our brain do to understand huge structures, complex structures? Because our brain is very, very well educated to deal with complexity in our world. And in cognitive science, there are three mechanisms that we use as humans to save time with complex structures, to deal with them. And I'm going to show you these three mechanisms: chunking, hierarchies, and schematas, and relate them directly with software systems. And then you know what you should do with your legacy code base to get back on into a good state of quality and technical depth. So the first thing is chunking. What are we doing? Our brain is doing chunking the whole time. So whatever we see around us, we try to connect things into higher things and put them together into higher chunks, bigger chunks. This is what you're doing the whole time when you're listening to me. My sentences are more than 7 or 9 words normally. I think so. And our brain can only keep 7 or 9 words separate from each other and remember them. And after that, you chunk. So you're chunking all the time. And it's a real cool mechanism because it helps us to abstract from things. But this only works if the things that we are chunking are related. They have a connection with each other. Just because they are close to each other, this doesn't really help. This picture here is a seal and a stone. What do we do if we want to chunk it? What is it? Beach? Not very specific. A beach for a seal and a stone. So we need things that are related to each other to be able to chunk stuff and put it into a higher symbol for ourselves. I will show you a class now, a Java class. The class has a very wonderful name, XY Manager. And what can you do with it? Okay, you can register services, you can get services, you can initialize a service registry. Okay, everything with services, this is nicely put together. Maybe we can chunk it. But then it goes on with an event queue. You can initialize it. You can send events. You can initialize even a printer queue and print documents. So this is a good example for a class that is very difficult to chunk. 3 different things in there that are not related at all with each other. And this already shows us the concept that we have in computer science that relates to chunking. We are always talking about modularity. We want software that is modular, and a well-formed architecture really follows modularity in this sense, in the sense of chunking. And if we think about modularity, we have different concepts or ideas that are related with that. I will show you now, but we will start with a little joke because it's so nice. One of them says, it's crucial to find a good name for your class which reveals its purpose. And then they look on the screen and the other one says, like crap, I don't know where else to put in. And the first one says, exactly. So this whole thing points to naming is key. Then if you can't give something a good name, it's not modular. This is actually the point, like we have seen with the seal and the stone. If you want to help people to chunk your classes, your packages, your modules in your projects or whatever, you need a good name. A good name should fall into your mind directly, and then your modularity is well done. A very good other concept that is related to modularity is high cohesion and low coupling. This is such a wonderful idea, and the best thing for me to explain to explain this is, if you imagine you have a package or a directory or a namespace in C# and C++, there are classes in there, and these classes together should have one responsibility, should work together and have a high cohesion. They should need each other to fulfill their task, but they should have loose coupling to the outside, because they don't need anything from the outside. They can do what they have to do together on their own. And this is the idea of high cohesion and loose coupling, and as well of responsibility-driven design, or the single responsibility principle of Robert Martin from the solid principles. So the idea of modularity is to build things that belong together. And I will show you another example to explain this on a higher level, above classes. Imagine you have a wonderful architecture. You have done it in the way we want to do it today. You have created bounded contexts from domain-driven design or microservices following the domain. So you have created a green module for the green domain and a purple module for the purple domain. And in there, they have layers, of course. You see the layers in there. And an orange module and a blue module. So you have 4 modules in your architecture. And then we look at the system, and I just decided to have a package tree, and we look at the package tree, and there we find this. So what you see here is a package tree. The uppermost package is at the top, and then you see how the tree is divided until the leaves down there. And if you look at it, you see, oh, what did happen here? The green one is on the left, okay, but oh, there are some orange and some purple packages that are spread all over the place. So this is not a very good idea to give people the chance to do chunking, to find the pieces that belong together. A better version with high cohesion would be to do it like this. Each of the modules finds its place. I can identify if I have to change something. I know where to go. I don't have to have in my head some kind of structure or a sheet to know which package is where. So here you really know where's the green part, where's the blue part, and where's the orange part. So if you have an idea of domain modules in your system, please put this structure as well into your source code, into your project structure, into your package namespace directory structure. It helps everybody to do the chunking afterwards, to find pieces and bits that belong together. So this was chunking at modularity. Hierarchies are a wonderful thing for human brains. Our brain is really, really good in remembering things in hierarchies. And this is what we want. We want people to remember a lot, to find their way around in the source code. Cognitive scientists have done a lot of research to measure how people can remember data, and it's very, very clear. Humans prefer hierarchies, and what we can do in our software is we can have hierarchies in there. I will show you what this means in software later, because the best thing that humans are doing is we are using something that the cognitive scientists call schemata. Schemata are ideas, concepts in our head that we know, where we know what this all means, and we have some examples of it. So if I tell you that my parents both were teachers, you might, the teacher schema pops up in your head, and you might think, oh, what a dreadful childhood she must have had with 2 teachers behind her back, which was not the case. My parents were very nice. Or you might think, oh, this is why she's talking so quickly and so much. So if I tell you my parents are teachers, your schema for teachers pops up. But if I tell you my father was a hammer, there's nothing. No schema in your head, because, or maybe you're thinking of a hammer, but this is not a word for a profession. Well, a hammer those were the people who, before we had trucks and lorries and trains and airplanes, who took the goods from one side of the Alps to the other side. They were called hammers, like this man on this photo here, very old photo. They don't exist anymore today. So I hope you had you understood, or you felt, or you saw now how schema can help to understand what is in front of you. You can understand much quicker what I'm talking about if you have schematas for the things I'm talking about. This is the one point. And the other thing is that schemata make us much quicker. So the cognitive science did a test. They took a chessboard, showed it to chess experts, and asked them to remember the setting of the stones on the board. And then they took the stones off and asked the chess experts to put the stones back as much as they could. And they did the same with people who don't know much about chess. And the result was the chess experts were able to put back double the number of stones than the people who don't understand anything about chess. But this only worked as long as the stones on the chessboard were set up in a reasonable setting for chess. If there was a nonsense setting on the board, everybody was the same. The experts didn't remember better than the non-chess experts. So what we learned from this is that schematas help us a lot to remember things, to understand things. The chess experts had their schematas for the setting of the stones on the board, and they took those settings and remembered much more with them. So what does this mean for software development? Well, we do have schemata in software development. We have a wonderful tool in software development that fits exactly with schemata, and this is pattern, design pattern, architectural pattern. They are really wonderful schemata that we can use in our systems to help people to understand what this part of the source code means. But the important point is that we use the design pattern and the architectural pattern consistently. Consistency is the most important thing. Imagine we are searching in a system like this. We have a model view controller. In the UI, we have a service, we have business objects and value objects. So we have well-known pattern in our source code. And the other day I was searching in a thing like this with a colleague. We were looking for a bug. We had a bug in the system, and we came down from view controller to the service. And in the service, we found a factory. I don't know if you know the factory pattern. This is a quite old pattern of the Gang of Four, which is in this very old, the first pattern book. And a factory is a class where you can ask for objects, like a factory is producing new objects. Today, we tend to use dependency injection, but in legacy code, you will find a lot of factories. And we looked at that factory, my young colleague and I, and we saw, oh, okay, you can create business objects, you can create value objects, but, oh, what is this? The factory class was as well able to calculate stuff and to save and process business objects to the database. This is something a factory should never do. We looked at it, and my young colleague said, well, this is really unbelievable. Who did this? We have to refactor it right away. And I said, well, okay, let's have a look. Maybe it's just the wrong name for that thing. Maybe someone started it as a factory or misunderstood the pattern. But the point here is not the misuse of the factory pattern, but the point is that our flow was gone. We flew through view, controller, service on our search for the bug. And then we stopped at the factory, and we couldn't go on because we had to understand what was happening here. Why did someone use the factory pattern not in a consistent way? So this is the important point about pattern. We have to use them consistently. we will look now into several software systems that I have seen, and I will try to make the point a bit stronger for you, what this whole means. And we will start with hierarchy, because I have not talked much about hierarchy. I don't know what your idea about software system is these days, but like 10 years ago, we started to stop just talking about technical layers, but we started to talk about domain modules that need some layering as well. So there's always a base layer in the technical sense, but also a base layer in the domain module sense. The basic functionality and some other functionality built on top. So this is something we wanted at the beginning of 2010. This was afterwards we have microservices, and that changed a bit, but this was already a challenge for most of the software development teams. And I will show you now a real architecture and try to explain to you what this means in those systems. So what I'm going to show you is a Java system of 170,000 lines of code. I think it had 170,000 lines of code the first time that I saw it, which is quite small. 170,000 is not a lot. And the architect of that team knew me quite well, and he knew what we could do. And he said, well, can you maybe come by for a day and look at the source code with the team and discuss the architecture, because we have to enhance the thing in the next year. And I'm not so sure if they have done the architecture right. And so we did, and we always use tools for that. And I will show you now what we found the second time we went there. Because after this one day of reorganizing everything and working on the technical layering, we worked on the technical layering a lot, and we created 40 refactorings or something. I told them, I will come back in a year. I will come back and you will show me your system again, enhanced, and we will look at the technical layering, but I want to have a domain layering as well. And now I will show you what I found, because it was a really, really nice result. And I will explain all the bits and pieces in this diagram to you. We modeled the technical layering and the domain layering. We will start with the technical layering, and I will explain to you the domain layering afterwards. What you see here is a view out of a tool that is called Sotograph. I will give you the reference to it later on if you want. So what does this tool do? All those tools for architecture analysis, they do a parsing of the source code, and they show you the structure afterwards, the structure that they find in the classes and in the packages. And this picture, or this diagram here, is already a second step. After you have the packages and classes in there and their relations, you start to model the architecture. And what we have done here is we have put the packages, or some packages, together into those square pieces, these modules there. You see all those square pieces, and then we put them into layers, and you can see the layers here too. If you look at the screen, you see like 8 or 10 squares, and then there is a light blue bar in between. So this upper part is the UI. Afterwards is a very big part of business logic, and down there is the data model and some other stuff. So this is how the technical layering is organized. And then there are the relations. And this is the interesting thing at the end in an architecture. Who is using whom and why and so on. And on the left side of the line, you see all these green arcs. All these green arcs are relationships that are inside of the system. So from the upmost square, in the upmost square, there is some class that needs some functionality from the square downstairs. So there's a class that calls a function or uses an object or whatsoever from the square down there. And if we would open the squares, we would see the package tree and the classes. So the green side, of course, is the good side, because all those relations, they follow the technical layering. But there is something which is not good. You see one red line, one red arc, and several yellow arcs. Well, The yellow ones, we changed the color from red to yellow, and I will explain in a second. But the first thing that we found was this huge red arc. And when we showed this to the architect, he said, "Oh, this is great. I knew it. Down there, this thing in the business logic, this is the reporting component. And I knew something was wrong, but now I see it. The reporting component is using something from the UI. This is absolutely impossible. Can I have this picture? I will show it to my management and I will get money to refactor the reporting component. This is really horrible what we have programmed here." Of course, we gave him the picture and he was able to get some money for this refactoring here. And the yellow ones were very funny. We looked into the square down there where one yellow arc starts, and we saw a class that was using the implementation class of a service up there in the business logic. And the architect looked at it and said, "Oh yeah, well, this is easy. It should be the interface. The interface is down here, and then there's no violation anymore." So we wrote it down, changed the color to yellow to tell each other, well, we have looked at that and it's easy to repair. Then we looked at the next one, and it was the same problem, the use of an implementation class, not of the interface. And we looked at the next one, and it was the same, and the same again. Well, what happened? Someone did copy and paste, of course. Someone copy and pasted the same piece of source code over and over again, which is quite normal as we program. This is, on the one hand, this is really nice because it's a pattern of a violation. It's a violation that comes again and again, and it's easy to repair because you know it's always the same. But if you don't find these things, then they grow more and more. They grow stronger and stronger. And in the end, you look at your source code and you think, wow, maybe it should be like this. So whenever you find stuff like that in your legacy source base, please use the scout rule. The scout rule means that if you, what are scouts doing? When scouts sleep at a place close to a river, they build up their tents whatsoever. The rule is that they have to clean up the place and leave it in a cleaner state than when they arrived. They really need to make it into a better place. And this is what you should do. Whenever you come across source code where you change something and you see technical debt, violations, stupid things, please repair them. You can't repair everything, but please repair the bits and pieces that you see on your way. This is the scout rule, and I think it's very, very helpful for legacy code. The other side of the slide is the domain layering. So layers of domain parts. On the bottom is the basic domain stuff. And on top, there are some other layers with other domain parts. And when we had modeled this, it's the same squares, we took the same squares and just reordered them in a different way. And you see a lot of green and a very little amount of red. So I really praised them. And I told them, you did a real good job. All the last year that you programmed, you remembered what I asked you for. And these little red arcs you will be able to repair. This is easy. So this was the good example. Now I will show you the bad example. Well, yeah. This is a system of 7 million lines of code. So it's much, much bigger. And when we came there, we started with the technical layering, as you can see on the left side. And if you look at it, well, it's quite green. There's only a little bit of red. But there is one other point that I didn't explain to you up to now. The darker square or rectangle is, the more is in there. So what you see here, actually, those rectangles, those are the layers of the system. In the other picture before, the layers were open and you could see what was in there. So what can we see here? Well, there is one layer that is quite dark, and this is like almost 7 million lines of code of the system. This is the business logic layer. And if you look inside, and this is what we did, you find something, oops, wrong. You find something on the right side that looks like this. You see, well, we didn't even do a layering here. We just asked the tool to organize the packages in there so that those that are only calling other stuff are on the top, and on the bottom, everything that is called all the time. So this what domain-driven design really calls a big ball of mud. This is everybody needs everything, and you can't take things apart and know where you are. And this is really a difficult thing that you find a lot in legacy code. I asked the architect, how does it work here? What are you doing? How are you deploying? And he said, well, we deploy 4 times a year, always on weekends, and everybody has to come, the users and the developers and the testers, and we try to get everything done on Saturday so that we can deploy Saturday night. If we are lucky. If we are not lucky, we are still here on Sunday. And I said, well, what is your plan if it doesn't work? I mean, you don't get a system that you can deploy. And he looked at me and he said, well, we are having a forward strategy. We don't go backwards. And well, I had to think about this for a while because it sounded so positive. But in the end, the thing he told me was, we have to deploy. My strategy for if it doesn't work, my strategy is not to deploy, but I will never do that. I always want to deploy because people need the features. We can only go forward. And this strategy is the only way he can do it because he has this big ball of mud inside of his system. He can't deploy bits and pieces. This doesn't work. Everything needs everything in this big ball of mud. And I look at this a lot as well on class level. So 10 years ago, I was working on a container terminal, and we had a C++ system to organize the stocking of the containers and everything. And I had the chance to look inside of this system. And this system inside on the class level looked like this. So what I found was 119 classes. So all these squares are classes in this diagram. And 119 of them came from 4 different components, and they were strongly connected. This is a class cycle. You cannot get anything away without the other stuff breaking apart or breaking down. And up there you see some other cycles, smaller ones. And I looked at it and I said to the company who produced this C++ software, please do something about it. This is not a good solution. This will grow and this will have a horrible effect because you don't know your way around anymore. And this company said, well, yeah, okay, if you pay us, we will work on the quality of this cycle. We will get rid of this cycle. But the boss of the container terminal was not amused. He said, well, I ordered high quality software system. I will not pay you for this. So they went off and said, okay, we do it sometime between. Well, 2 years later, the thing looked like this. Now you can see 327 classes tangled together from 8 different components. And this is really hard to get apart again. And whatever you do, whatever you program outside or wherever you change any class or put in a new class, it will fall into this cycle. They are like black holes. They are pulling classes inside. And this looks as well like this because in the middle, in the center of the diagram, it's dark, it's black. And you know why? Because there are so many dependencies between the classes that the tool could only print a black area in the end. So this is what really happens in old systems, and you have to be aware of it. You have to be careful. You have to do something about it, because otherwise you will end up with this feeling. I really love this one. The one programmer says, oh, I cannot reproduce the bug from yesterday. And then they look at each other, and then the other one says, well, maybe a time-space discontinuity has come by and moved us into a parallel universe where this bug has never existed. And then they turn around, and the first one says, oh, sounds reasonable. I close this ticket. This is the feeling, this is how it ends up if you have a lot of cycles in your software. So please don't do it. Try to create things that are hierarchical. You will know what is at the bottom and what is built on top and who should do what. And we will look now into modularity as the next concept of how a well-formed structure should look like. And of course, you can start on a very easy level. You can just measure the size of your classes, of your files. There are a lot of tools that help you with that. If you use SonarCube or some other dashboard that measures the sizes of things, it's very easy. What you see here is you see from a tool as well the number of files with a certain size. And this tool says, well, you should not have more than 1,000 lines of code. And you can see for this system that most of the files are smaller than 1,000 lines of code. There are only some classes that are, or some files that are bigger. And then, of course, we have to work on the big ones. The diagram in the middle shows how many methods are there with more than 100 lines of code. It's very easy. You can see directly what is too long, too big, and you can work on that. And the last one is a very nice a metric as well. It measures how complex methods are. What this metric does, it counts how many paths you can find in a method. And of course, if you want to repair something, change something, you have to think about all the possibilities that you find in one method. And it should not be more than 10. And this system is quite okay because most of it is under 10. But there is some method that has 119 paths. This starts to be complicated. You know, I have seen one system with a method with a cyclic complexity of 637. So this was quite complex and difficult to understand. So just measure all that stuff and work on the things that fall out of the normal range. This is a very good rule as well. What I do a lot is as well, I look at I look at into the systems if the modules are of even size. And if I find something like this, a monolith of almost 1 million lines of code and then some little satellites around, then I know already something is wrong here. Why did they do this? Why did they create such a big module and small modules around? And the other day I saw a system and someone explained to me why this happened. This was a system that was built at a time when we didn't have Maven or anything similar like that, but this was a system built in Java, and it worked on a basis of something that was almost like Maven. So they had built into it the idea or the check that cycles were not allowed. And I asked them, well, how is your architecture? And they said, well, we have 9 components. And I said, okay, let's design them. Let's create them in our tool here. And they said, well, yes, but can we maybe do it the right way? And I said, well, what is the right way? Well, we have actually 19. I said 17, not 19, 17. And I said, well, show me. And this is a different tool again, but you will understand very quickly all those packaged symbols are modules, all those. So what can you see here? There are 5 orange ones on the top. Then there are 4 green ones and 5 blue ones, light blue, 2 dark blue, and 1 purple one. So this is 17 subsystems. But the 9 components that they had, because they had to follow a rule of no cycles in between components, are the orange ones on the top, the one green one and the light blue one on the side, and the dotted lines, they are the big component that has all the other little subsystems in them that they actually wanted in their architecture. But if you look at it, I have surrounded all those arcs that are cyclic arcs, where one subsystem uses another. So this was the reason why their system was organized in such a strange manner. And of course, we discussed it, and they told me, well, we built our system before this rule of no cycles between components was created, and now we don't get any money to refactor it. So if you have things like this, if you have Maven modules that are really huge and other that are really small, look at it. Ask yourself why your system is so unevenly balanced. This is actually not a good idea. The other day, we went to a company with 9 million lines of Java code, and they said, well, we heard about you. They say that you can do interesting things, but we don't have much money or time. Come a day and look at it. Well, for 9 million, this is not much time. But we took the challenge and we looked at it. And the first thing that I asked them was, well, how many build units do you have? And they said, well, we have 126. Well, this is not enough, or 128. Today I have a -2 +2 problem, I think. Well, 128 build units. And the first thing we did is we measured the number of classes per build unit. And as you can see here, there was one build unit with 9,240 classes. So really huge. Often just one system has so many classes. So this is really huge. And this is sort of a sign of some problem normally. So we looked inside and we found out, oh, this one thing has 3 million lines of code. This is a lot. And 3 million lines of code is a third of the system. And if you look at the diagram, well, from the number of classes is less than a third of the system, which means that those classes are bigger in this build unit than in the others. And we knew we have to look in there. So we looked in there, and there we found something that I have never seen before. We found a class cycle of 5,270 classes. Really, really huge. And if you look at it, it's all squeezed together even. So there must be a lot of relationships, a lot of dependencies in there. And I looked at it and I said to the architect, wow, what is this? What did you do here? How do you work with this? How do you change things in there? And he looked at me and said, we don't touch it anymore. We have built an interface. So the purple stuff up there is the interface. In domain-driven design, we call this an well, I lost the word, but a layer not to interfere into us. You probably know the word. It will come to me later. Okay, so this is really horrible. And if you can do anything, just don't arrive at this state, or try to do something to get out of this situation as soon as you can. Start to get test cases in there. Start to get classes apart. In this case, of course, you can't start on the class level. You have to start on an architecture level and get the things apart. Another point is the getting apart the architecture from a domain point of view. Because before I talked on the class level and on the technical layering, but the domain layering is very, very important in large systems, of course. And the most difficult thing with huge code bases is that we try to create domain modules in there, but the part of the system where the most dependencies exist are with the domain model on the bottom. The domain classes like product, client, account, or whatever you have, contract, whatever the basic domain model is in your system. This is the point where the most systems are highly connected. And I will show you an example now how this could look like. This was a system where the architect called us and said, well, I need help. I want to divide my systems into microservices. Can you help us? And I said, well, what do you have? And he said, well, we have 1 million lines of Java code, which is big enough to cut it into pieces, of course, into microservices. And I asked them, well, what is your architecture? And normally the answer is we have layers, which is normally technical layers. And then I know already this will get difficult. But this guy said, well, our architecture is use case driven. We have use cases. Oh, I said, well, this could be possible. So we went there and we tried to divide the system into use cases to have a domain module architecture. And what you can see here are the use cases, of course, not the real names, but the real structure. And you have mailing, import, export, remove, startup, reporting, editing, and so on. And on the right side, you can see the arcs. The color is not important in this case, but you can see maybe, okay, mailing, import, export, and remove, they need each other. They maybe could form a microservice. And startup and reporting, and well, editing is alone, and so on. And then I said, but if I look at it, what is this down here? Model. Oh, the customer said, well, this is our domain model. In there are customer, product, contract, and so on. And I said, well, listen, if we want to divide your system into domain modules, we have to get this thing apart. Can we maybe move those model classes to the use cases where they belong to? Yeah, maybe we could try. And then we did. We moved the classes upside into their use case layers. And the result, I mean, I think we stopped at calculation because the result looked like this then already. And here you see how the domain model is creating dependencies between all bits and pieces in the software. So this is very important to remember. We all learned that our domain model, that we should reuse classes. And this is opposite to what we want to do in a microservice architecture. So if you have a domain, a code base like this, where the domain model is highly reused from everywhere, there will be a lot of work to get that apart. And you should really think about if you want microservices, because you will end somewhere in this diagram that I stole from Simon Brown. What you can see here is, well, if you have a monolith, which is a big ball of mud, you can try to cut this into pieces, but you will end up with a distributed big ball of mud if you just increase the number of deployment units. This will make the problem even worse because you have to search for dependencies in the distributed world and not in the monolith. The best thing is to move your monolith towards a modular monolith, which you find up on the top, and then maybe move to microservices. Okay, and the last thing is pattern consistency. If you have pattern in your source code, this is a very, very, very good idea. This helps people a lot to understand what you are programming. We have, again, model view controller, service, entity. Now I'm using the domain-driven design terms, entity and value objects. And if you have this in your source code, this is really wonderful, because what do patterns do? Patterns help you to understand what is the responsibility of a class. What does a service class do in opposite to an entity class or a controller? They have different jobs to do in my architecture, and patterns form a hierarchy. You can see that all the arrows go downwards, and of course, you would be surprised if the service would call the view this is something which is not allowed. So if you have patterns, please talk about them. Talk about them in your development team and write down what these patterns are doing and where they are for. I will show you now a good example how patterns can be used. This is a server part of a system. And what we have done is we discussed the patterns with the team on a board. And then we modeled this into the software with a tool. So what we did is we collected all the service classes and put them together in this service layer and all the processor classes and so on. And because all these patterns normally form a hierarchy, you see here a very good example. Of course, I have bad ones where there are a lot of red arcs, and then we work on them with a team. But this is a good example. We were able to put 90% of the source code and assign them to patterns, and we only have a low rate of violations. And this helps so much because programmers program on the pattern, on the class level, and there are patterns. So please, if your legacy code base has patterns, work on them, get them right, discuss them, and try to convert those classes that don't belong to patterns at the moment into pattern classes. This is really, really a good strategy. I will skip one slide and show you this wonderful joke here, which I love so much. It is about best practice in application architecture. Today, use layers to decouple. And then one of them says to the other, and every year we mount a new layer to decouple us from the crap we've done the year before. And then down there, this is the wonderful thing, it says annual rings. So they have created annual rings for their architecture. And this is always reminding me of one meeting in a company where I had looked at 1 million lines of code, and we were sitting there with the architect and the IT boss of the company, and I said, well, listen, you are using a lot of patterns. It's a bit too much. You should reduce them. There are a lot of patterns that do the same, or they are not really good defined, and so on. And the architect said, yes, I understand, but you know, we can't change it. And I said, what? Why can't you? Well, listen, our software developers, they are architects. They have to invent new patterns every year. Otherwise, they don't find joy in their work anymore. And this is why we have so many patterns, and we can't get rid of them. We have annual rings. And this was, again, a moment where I looked at someone and thought, well, he is using a positive connotation. Annual rings on trees should be big and nice, but for software, this is not a good idea. People should not create every year a new big layer of new patterns. Of course, software has annual rings, but it's not a good idea. You should reduce that as much as possible. And now I will skip some slides. Yeah. Oh, yeah. Here I am. Okay. Yeah, there are a lot of tools that you can use for this. There are commercial tools. They cost money, and with them you can do these things that I'm doing. You can work on the architecture, change it, try out things, and discuss what is right. There are non-commercial tools, free tools that you can use, but they only show you the situation in the software. And we are doing this a lot in meetings with the teams. We are discussing their architecture. We are actually doing architectural work with them to find out how their source code should be, how it should look better. And in the end, we try to give the system one number to convince the management that they should do something about the architecture, or it's all fine. If what you see here is the Modularity Maturity Index, from 0 to 10, 10 is the best. So if you're between 8 and 10, you are green. You're in the area where you are still in a good shape. You are in the low corridor of maintenance cost. And you see some huge systems in there. From 8 to 4, you are yellow. There is hope, and under 4 you are red, and this is a real problem. You should do a lot with systems that are red. You have a lot of work to get up into the green area. The yellow ones, there's more hope, but there is a lot to do to get into a modular state to become green. And I hope that you don't go away like this today, but you enjoyed what I was talking about. And if you want to know more, just read my book, write me an email, talk to me on Twitter, or look at the website of the book, and I will answer your questions afterwards if you want. Thank you.
Yeah, thank you very much, Carola. I think we'll go to the break. We have a few questions.
Yes.
I don't know, Adi, do we tackle the questions or do we move them?
Well, I can answer the 2 ones that I see here with 2 votes quite quickly if you want.
Please go ahead, please.
Yeah. So the first question is, was the tagging of the objects into layers done manually? It depends. Normally we don't do it manually, but we just take packages, or we take patterns, name patterns, and if the architecture is done right, you can even do it with regular expressions. So doing it manually is horrible. And the tool, I write it into the chat, is called Sotograph. But I will put my sites online. You will find all the information, and you can ask me on Twitter if you want.
All right, that's perfect. Thank you very much, Carola.